Okay, good morning. So, we will get started today. Last time we were discussing about Windows and Unix and their use in real time applications, what difficulties will arise. So, today we will complete our discussion on using Windows and Unix on real time applications. We had left some parts, and then we will look at real time POSIX, which has become a standard in real time operating systems. Actually, initially it was designed for Unix based operating systems, but now it is a standard for all operating systems. So, let us proceed. So, today we will first complete our discussions on using Windows as real time operating system. We had looked at Unix, and then we will compare the Windows and Unix features for use as real time operating system. And after that we shall start discussing about real time POSIX. So, yesterday we were discussing about Windows and their evolution. We had seen that started in 1982 as a simple disk operating system and kept on evolving, and major event was a graphical interface Windows 1.x, still single tasking and simple operating system, and slowly it evolved and more features were incorporated, and the code finally became unmanageable because it was basically a maintenance on some old code, successive maintenance. The structure of the code degraded and the code was discontinued, Windows 98. But by that time they had started the Windows NT. This was a freshly written new code, and as we were pointing out, it is a microkernel based operating system. The idea is to tackle the bugs. Earlier we were saying, I think Windows 95, 50,000 known bugs, but could not be debugged. So, Windows NT has become stable. It is a stable operating system, does not crash as Windows 95 or 98 used to do, and that is keeping on evolving. Now, let us see how this NT series is suitable for real time applications. The earlier series there was no question of using it in real time applications because it was unstable. So, the Windows code was completely rewritten and the NT system was developed, and even though it is microkernel based design, but we will see that it is more of a layered design than a microkernel design. We will see that. It is much more stable, and all the later versions, these are descendants of the Windows NT code, and the DOS based code was scrapped. So, let us see the Windows NT, the main features, and let us examine how suitable it is for real time applications. So, the microkernel here provides the basic services, and on top of the microkernel we have the executive, which builds on the basic services to provide user level services, and these user level services are used both by the privileged subsystem, which is part of the OS, and also by user programs. So, if we look at the structure of Windows NT, we will see that in the kernel mode we have the microkernel, and on top of that is the executive. In a pure microkernel design, we were discussing, I think last time, that the kernel mode only the microkernel operates, and all other operating system components they operate in user mode. That is the basic of a microkernel based design. So, it is not purely a microkernel design, it is a layered design. See, the executive also operates in kernel mode, but it provides higher level services then the microkernel, and the microkernel is the one which interacts with the hardware, and there are two types of interfaces here, the Win32 interface and the POSIX. We'll discuss about POSIX today, that is the main focus of today's discussion, and the user level processes can run using both these interfaces. So, the executive, as we were saying, it provides higher level services than the microkernel, and the executive also runs in the kernel mode, which is not a purely microkernel based design, but the executive is completely separate from the microkernel itself, it just calls the microkernel. But still, because these are two separate things, the microkernel and the executive, it is easier to maintain, unlike the earlier code DOS, and from that the 95, 98, which was a monolithic code. Here is more layered here, and we have but still both of them operate in the kernel mode, and the executive is actually preemptible and pageable, whereas the microkernel is not. So, there is a difference here also in the features of microkernel and the executive. The microkernel is memory resident, it is loaded the start, whereas the executive is pageable and also preemptible. So, it provides 32 levels of priority, which are divided into three classes of priority, two classes, dynamic and real time class, and we also have an idle class, we will come to that later. So, there are two main classes here, the real time and the dynamic class, and we know what is a real time priority level, isn't it? What is a real time priority level? Anybody would like to answer? What is a real time priority level and what is a dynamic priority level? Sorry? Static. Okay, and dynamic?
Change depending on
okay. So, the real time priority levels, they do not change with time, and these priority levels are assigned to the real time tasks, where the average throughput is not a concern. The main concern is meeting task deadlines, whereas in a dynamic class, the tasks that run here, they do not have deadlines, and the concern here is average throughput. So, the operating system keeps on changing the priority of the tasks that we were discussing yesterday, and once a task is assigned either of these priorities, it cannot move between these two. So, once it is a real time priority, it will continue to be real time priority. And for the dynamic class, the priority level of the task keeps on changing. For example, if there is a task running and you iconify, there will be a change in the priority, and also it depends on whether it is using CPU time or is doing IO, and besides that, if you iconify also, it might change its priority, it will change its priority. Now, let us see the priority levels supported by NT. So, there are basically two main categories of priorities. In the real time, there are subclasses here, real time idle, normal and critical. You can assign priorities at this level, and in the dynamic, high foreground, normal foreground, normal background and low foreground, and within this the task, this band of priority, the task operates unless you change a background task into foreground and so on. And the lowest priority is the idle task, and this is a non-migrating priority. Again, it is like it is also a static priority, it does not change here. Now, one important thing that we need to discuss is about interrupt handling in Windows NT. We will see that the feature that we are looking for, we were discussing, is required for real time operating system, is present here, but still there is a small problem here. Let us see how the interrupts are handled here. So, once interrupt occurs, the handler routine saves the machine state and makes the system execute the interrupt service routine. But in the interrupt service routine, only the critical processing is performed, and the bulk of the processing is queued as a task in the form of a deferred procedure call or a DPC. So, we are saying that this is required for quick response to interrupts. So, that feature is there. Now, let us look at the XP derivative again of the NT. It is a layered architecture. Executive runs in protected mode just like the NT, provides the basic system services, and on top of the executive several services operate on user mode, and additional services can be added without affecting the executive. So, which will operate in the user mode. So, based on the executive, more services can be added which will operate on the user mode. It is portable across hardware architectures with only few changes, written in C++. The processor dependent code, the microkernel basically, is isolated in a dynamic link library called as a hardware abstraction layer. Again, the same feature is there, right, as NT. The kernel is never paged out of memory, and its execution is not preempted, and the main responsibility of the microkernel is thread scheduling, interrupt and exception handling, synchronization, and recovery after power failure, and based on this the executive and the user tasks operate. Similar feature just like NT, because after all it is a derivative of NT. So, let us not spend time on discussing this. Now, let us look at the feature of the deferred procedure call. We said that the interrupt handling is much better than Unix, the basic Unix. Here the bulk of the processing is done in deferred procedure call, but let us examine it further. So, once the interrupt is handled, the deferred procedure calls are queued in a FIFO manner, in a FIFO queue. And one catch here, just see here, the DPCs are processed at the same priority level, irrespective of which task or the interrupt corresponds to which task. All of them are treated in the same manner, or in other words, even unimportant DPCs can affect execution of a real time thread, because these are independent of task priorities. So, the DPCs for a real time thread will operate at the same priority as some unimportant task, for example, some email or something, or maybe a disk IO, just logging something onto disk, they will operate at the same level. This is just an example here, the problem that might occur. The page faults of a low priority process like logging or something can execute at a higher priority than a real time process. So, this is one of the main problem that you would face if you want to use the NT or its derivatives in real time applications. For example, if we have tasks performing network or disk IO, unimportant tasks, then for the real time tasks they will translate into unbounded response time. So, using the, even though the NT series has many good features, freshly designed microkernel based and DPCs and so on, but still there are problems here which prevent its use in hard real time applications. But the Windows CE, which we will discuss some extent later, which is used in embedded application, this provides a priority inheritance of the DPCs. So, we had looked at the priority inheritance earlier, that DPC of a higher priority task should inherit the priority of that task. So, typically the DPCs operate at a priority level normal, and if the task has higher priority than normal, then the DPC will inherit the priority of that process. So, the major shortcomings of Windows NT for real time applications is unpredictable interrupt handling, because of these DPCs operate at the same level, weak resource access control. So, it is still possible for tasks to use each other resources, that is inherited from the DOS series. Poor support for distributed applications, and the unpredictable interrupt handling, we had seen that it can cause unbounded priority inversions, and weak resource access control does not support even the basic inheritance scheme. So, there is no real time resource sharing is not supported. But if we compare NT and Unix for real time applications, we will see that the DPCs are supported by Windows NT. So, the response time, interrupt response time is much better here compared to Unix System 5. There are real time priority classes, we had seen that, whereas Unix there are no real time priorities, all are dynamic priority levels. Timer precision is 1 millisecond, Unix 10 millisecond. Asynchronous IO supported in NT, not supported in Unix 5. We know all what is asynchronous IO, isn't it? Okay. Memory locking is supported. So, this is an important feature to reduce the jitter in memory access. If there is a page fault, then the memory access time can be really large, and for real time tasks that would be unacceptable. So, the memory locking facility is also provided in Windows NT. So, has many positive features. So, it is much suited. Okay. So, I think let me just elaborate on that. See, last time we discussed about that. Since you are asking, let me just elaborate on that. So, we said that if the data or the page that is needed is resident in the memory, then it just you get it instantly, isn't it? But if there is a page fault, then you have to fetch it from the hard disk. So, the time can be a second or maybe a fraction of a second. So, the real time tasks, they can lock certain parts of their memory which will never be paged, and they can even lock their entire address space. So, that gives deterministic memory access time, right. Okay. So, as we can see from this comparison table, that if you are thinking of a real time application, the NT is much suited than Unix as it is, but we will see that again the Linux has good features. So, this is the Unix System 5, which was designed to be used in traditional applications, and that too in servers, right. So, naturally this was not designed for real time application, and it does not support those features. So, let us just try to answer one or two questions. So, what is the difference between a monolithic kernel and a microkernel?
Monolithic kernel has the
entire kernel into the main memory, while microkernel has only basic kernel.
Anybody would like to answer differently?
as the
Microkernel has only basic services in kernel mode.
Yeah, exactly, kernel mode. So, in the kernel mode, the basic services are provided in the microkernel based operating system, and all other operating system services are built on the microkernel operating system, the microkernel, but those operate at the user mode. Whereas in a monolithic kernel, all the operating system services are provided they operate in the kernel mode. But what are their relative advantages?
small part resident.
But how does that help?
Easy to maintain.
I mean, why is it easy to maintain?
Only small part is there.
Sorry?
More user programs can.
No, why is, see, microkernel based operating systems are easier to change and extend, true, but why?
Debugging that part.
Layered architecture and modularity.
No, even the traditional, the monolithic kernels are also layered architecture. It is not that everything operates at the same layer. Layered architecture is not the answer.
Modifications, it's easier in a microkernel. As it is
Why? Why debugging is easier? Yes, correct debugging. Sorry?
As it is smaller.
Not really. See, anything that operates in the kernel mode, debugging is difficult, because a kernel mode task can change anything, any data anywhere, right? So, and also you can't use a debugger in a kernel mode. So, debugging a kernel task is always difficult, and this is a small microkernel which can be developed, debugged and extended, maintained, etc. Whereas in a monolithic kernel, just see, everything operates, the large operating system, millions of lines of code in the kernel mode, and it is really a nightmare to debug a monolithic kernel. So, one is about developing, maintaining, etc. Microkernel is easier, because most of the services operate at user level, like a normal application, right? But what are the any other advantages of the microkernel approach?
If you are operating in two modes, you can make one mode as protective.
Not clear. Can you elaborate your answer?
The kernel mode is protective mode.
Yes, it is protective mode, same in monolithic.
Second task will be non-preemptive.
No, kernel mode, okay. So, you are saying that even without using kernel level locks, we can just disable the interrupts in a microkernel and still not have difficulty, is it? Okay, possible. So, he says that the microkernel, we do not need the kernel level locks, because after all this provides only the basic services, and that does not take much time. Possible, yes. We will see that some of the operating systems, microkernel based ones, they do not use locks. Okay, any other advantage of microkernel operating system?
Microkernel OS has separate file servers and separate that operate in user mode. So it might help in easy accessing of that file servers, because we need not switch to kernel mode.
No, see, any service, finally the user mode component, operating system component, has to invoke the microkernel. So, there has to be a mode change. It is not that you can give services without mode change. So, okay. So, another advantage can be a lower interrupt response time, okay, because of the low code overhead. But what about disadvantages?
It has to make two calls.
Yeah, it is inefficient. The microkernel operating systems are inefficient because it makes two function calls, one to the user level process, which in turn calls the kernel, the microkernel, and also the mode changes and more here. Okay, now let us go to the next question. Why traditional operating systems dynamically change task priorities? Yeah, exactly. They change the task priorities at the every time slice, at the end of every time slice, because the IO bound processes have to given a higher priority. So, if something is doing IO, its priority keeps on increasing, and if it is a CPU bound task, its priority keeps on decreasing. The idea is that the IO channels should be kept busy, so that the average response time improves. Okay, so let us look at this question. What is the advantage and disadvantage of having a memory protection support in a real time application? Advantages, okay, I think it is simpler question. What is the advantage of having memory protection support in a real time application? No, memory protection, not memory locking. Memory protection. Basically, one task can't access the memory, the data and the code of another task. It is easier to develop. Advantage is that if there is a memory protection, it becomes easier to develop debug. There is no memory protection, you do not know which data it corrupts, right. But what about the disadvantage? Because we will see that there are some operating systems which real time which do not provide memory protection.
Then for each task we need to maintain separate its own memory. There has to be bounds between memories of two different tasks.
No.
So extra maintenance, extra code has to be dedicated for it.
That is a disadvantage you are saying, is it? No, not like that, because see, if you make it work once, it will keep on working. It is not that you need overhead each time you do something, not necessary. So, any other advantage or disadvantage of, okay, let us look at the disadvantage. Advantage you said, okay, easier to develop. What about disadvantage of memory protection?
So data sharing of tasks.
No, data sharing will be supported, that is irrespective of memory protection. That is supported as a, I mean, see, memory protection means you can also disable memory protection. You can allow another task to access. Okay, that is, sorry. No, not really. So, the simple thing, not that difficult, is that there is overhead. Each time the operating system checks about the protection data. You know the traditional operating system, a virtual memory environment. The protection data, the protection bit is checked. The protection bit is checked, isn't it? So, now let us look at the real time POSIX. POSIX stands for Portable Operating System Interface, but that gives POSI, isn't it? POSI, but what about X? Yeah, okay, I think some of you know this. This was developed to be a Unix standard, and to make it sound like a Unix standard, POSIX X was added here, Portable Operating System Interface. So, the idea here was to reduce the development cost and time. We will see why and how. Increase the availability of Arden packages, increase ease of use, and facilitate system integration and porting. That was the basic objective with which the POSIX was formulated. to reduce any application development cost and time. Later I will ask you how, once we look at the real time POSIX standard, how will this lead to reduced development cost and time, how it will increase the availability of RDON packages, how it will increase the ease of use, how it will facilitate system integration and porting. So, just have these questions in mind, because I am going to ask you after we look at the POSIX features. I am just going to ask you that how these occur, how these happen. Let us look at the genesis of POSIX, or the origin, how the POSIX came about. We had seen so far that Unix was developed at AT&T 1968 or 69 and was made a freeware 1975. The source code was given away, and since the source code was available, many vendors extended Unix in different ways. IBM had its AIX operating system, a derivative of Unix, on which they added several other features they thought appropriate. HP UX, many features they thought appropriate, they added to the basic Unix. Sun, they had the Sun OS, and then from that the Solaris, which is again a extension of the Unix in their own way. The Digital Electronic Corporation, they had their Ultrix operating system, again a derivative of Unix, extended whatever they thought right, they are appropriate for them, they extended Unix that way. The SCO with the SCO Unix, but the thing is that even though all are Unix derivatives, an application written on AIX will not work on HP UX, because they use different services. Not only the semantics, the syntax of the service is different. I mean, some services are not supported in other operating system, and even the services that are supported, the syntax may be different or the semantics may be different. So, if we look at the Unix versions, the Unix had its origin in Multics, and which is a derivative of the CTSS operating system, first time sharing operating system developed at MIT lab. It is not a commercial operating system, it is a educational institute developed it, and based on that all these are derivatives. And see here, from Unix we had this BSD developed at University of California at Berkeley, the Genix, the Sun Solaris, the Linux, the virtual memory operating system VM at IBM, and so on. So, again some of these arrows I have not shown, these are more complicated arrows, they have taken features from each other. But the end thing is that they have extended the basic Unix here in very different ways, and they have become inconsistent. Application written for Solaris will not run on Linux, not run on System 5, not run on VM. So, that was the situation. So, program written on one Unix, one version of Unix will not run on another, and the different versions offer different services. So, some services are supported in some versions, some services not supported. The syntax was different, even the semantics was different, and the need for a standard Unix was recognized. So, the first effort towards Unix standardization was done by AT&T. So, they found that even though they had made Unix freeware, one source code they had distributed, but it has developed in many different ways. So, they started this initiative. System 5 interface definition. They said, see, since the Unix was started by them, so they said their own System 5 with, of course, suggestions from other vendors of Unix should become a standard. But the SVID was ignored by other vendors, even BSD and other vendors, they ignored the SVID initiative. They said, see, we have developed in our own way, so there is no point why we should follow your own System 5 interface definition. Later, the ANSI, under ANSI and IEEE initiative in 1990, the POSIX movement came. The POSIX has become a IEEE standard, IEEE 1003. But before we understand the POSIX, let us see what is an open system. What do you think is an open system? Must have heard about open systems in the context of computer. Yes, anybody would like to say what is an open system? That is open source. Anybody at all would like to? Sorry? Flexible hardware support. What sort of flexibility?
Any kind of drivers can be installed over it. Minimal support of the hardware.
Minimal support, no, not very convincing, doesn't appear right. Anyway, let us proceed, because these are important terms, you hear them once in a while, even in newspapers or in general conversation. So, let us see this. An open system is a vendor neutral system. It allows the user to intermix hardware, software and networking solution from different vendors. So, if we have an open system, we can get one part from one vendor, another part from another vendor and so on. The user can use that, can easily integrate this, they talk to each other. But if it is not an open system, then they have to buy specific component from specific vendor. Other vendors can't even manufacture. So, there has to be standard interfaces for similar products. This has advantage, isn't it? If there is a standard interface for similar products, then there is a advantage. For example, just a common example, let us say you have a bicycle and the nuts and or let us say the pedal. If the pedals of a different manufacturer is different, you have to buy only that pedal, that will work on that cycle, other if you buy any other pedal it will not work. So, then it becomes difficult for the user, isn't it? And the cost also the user pays more, because that manufacturer, you will hike his price. Now, there are many manufacturers who manufacture that pedal. So, the cost will be less. So, the solution from one vendor can be used in place of another. Very powerful thing actually, open systems. I will just tell you a small incident after we look at this. So, it is clear that open systems are not copyrighted, anybody can manufacture components with the specific interface and saves the users and vendors from expensive IPR lawsuits, because if the interfaces were copyrighted, what would happen is that if the user brought a component manufactured by some other vendor or some vendor manufactured according to that interface, there will be problem. The open systems help interoperability of components manufactured by different vendors and also portability. You can use different components in different manufactured in different situations for another new application, that is what is portability. And we will see that POSIX is a offshoot of this open system movement. Yeah, I was just wanting to tell you one incident, how the open system is a very powerful concept. Before the PCs, I mean at the time the PCs came, 1980s or so, the most popular desktop computer was a Macintosh computer, Mac. It was called as Mac from Apple, and you would find, at least not that time in India, computers are not so popular, but if you go to western side, you will see that every secretary, everybody has a Mac on his desktop. So starting from secretarial job to everything they used to do on the Mac. But the Mac is a closed architecture, you do not know what is there inside, and the hardware, the software, etc., nothing was known. But that time the PC, which came in 1982 or 81, it appeared like a ugly box in front of Mac. Mac had a nice user interface, graphical, good sound, multimedia, but the PC appeared like a ugly box, large one, huge. Mac was a small one, huge box, and used to make very ugly sounds. But in 4 or 5 years down, you will think that time, let us see, these boxes are of no comparison with Mac, these will just die out. But in 4 or 5 years time, the Mac became obsolete. What is the reason? The PC was a open hardware, right? You can just plug in a card. So different manufacturers, different vendors, they developed different cards, and on the motherboard you could attach those cards, for example video processing, or example for a specific embedded application, or let us say you want to have a sound recording, very different types of applications. The vendors could manufacture many kinds of applications, they became available on the PC because it was a open architecture. Everybody knew what are the components, what are the interfaces, not copyrighted, anybody can manufacture and just attach cards on the board and it works. Whereas in Macintosh they could not do that, it was not open, you have to use those, and if you really wanted something you will have to request Apple. And as a result, the number of applications that were available on the PC, IBM PC, kept on growing phenomenally, and the Mac could not compete. Soon, in 4 or 5 years, the PC had changed its shape, it had become very powerful, many applications available, cost had dropped. So open system is a very powerful concept. But what is the difference between an open system and an open software? Are they the same? No, open system and open software are not the same. Open software is basically a free software, like you were saying open source. Open software is open source software, where the source code is distributed. Unix is a open software, but just see that even though it was a open software, it did not lead to, it was not leading to an open system, I am sorry. Even though it was a open software, it was not leading to an open system. I should have written here system. Unix was not an open system, because different vendors had they extended it in different ways. Anyway, so let us proceed with our discussion. The major concern for POSIX was portability of applications across platforms at the source code level, because that time the different versions of Unix manufactured by different vendors, application written by a programmer will not work on another Unix, considerable rework is necessary. So the major concern is that an application written on one platform should work on another platform, at least at the source code level, because object code level is difficult to provide portability, isn't it? Yes or no? Why is it difficult? Why at object code level portability is difficult?
Because it depends
Exactly. So, at the object code level, it depends on the hardware, specific hardware on which the object code is targeted, and if it is meant for a Intel processor, it won't work on a Sun processor because their instruction set is different. So, at least for at the source code level, it should be portable, and it was a huge success. Now, POSIX is so widely accepted that even though it was initially developed for Unix operating systems, different variants of Unix operating system, now even non-Unix operating systems make themselves compliant to POSIX, because otherwise the users will ignore them, right. They have their applications running across different platforms. So, they would try to use those platforms and ignore those which are not POSIX compliant. So, POSIX is now a IEEE and ISO standard. So, these are the standard numbers here given, the IEEE PE 103 and ISO IEC 9945 standard. Let us look at the overview of POSIX. One thing we must be clear is that it is not an operating system by itself. It only defines the interfaces of the system services. That is, what should be the name of the service and what should be the arguments for this service and what is the semantics of this service, right. These named services have to be supported and they would take this data and provide this result. It is not an operating system by itself, POSIX, but it just is a definition of the interface of the operating system, interface of the operating system services. So, not only the data or the argument, that is the interface of the services, but also the semantics, what exactly they should do and the result they would return. But it does not specify how exactly a vendor would implement the service. For example, can he use threads to implement service, multi-threaded services? So, can it be just one thread? Nothing is specified. The implementation is up to the vendor as long as the interface and the semantics are the same. The POSIX actually came up with several documents. POSIX point 1 is about the system interfaces, which we are discussing, that the services and their semantics and so on. POSIX point 2 is about the sales and utilities, because after all it was a Unix initiative. Then POSIX point 3, this is another volume, a document which says test methods for verifying POSIX conformance. If you look at operating system, how do you determine that it is POSIX conformance? What tests you need to do? So, this defines that. And the POSIX point 4, this is the real time extensions. This is our main concern in our discussion. This volume, the POSIX 4. But one thing we should keep in mind as we proceed with our discussion, that the embedded systems, they operate under various constraints, power, memory, etc., even the processor speed. So, many of these embedded operating systems, they actually support only a subset of the POSIX functionalities. And considering that the POSIX, the real time POSIX had become slightly irrelevant to the embedded real time operating systems, later the real time working group identified 4 application environment profiles and standards were defined for these different profiles. So, let us see the profiles. Achha, so that we will look at the next slide. Now, let us look at the POSIX document that are relevant to real time applications. One is of course the POSIX point 4 volume, which deals with the real time extensions to the POSIX operating system interface. The POSIX 4 defines interfaces to support portability of real time application. This is the most important document as far as we are concerned. The POSIX 4a document, it deals with thread extensions, because the embedded and the real-time applications are multi-threaded rather than multi-process. Multi-thread has a special advantage here for real-time applications. What is the advantage of a multi-thread compared to a multi-process?
Faster context.
Yeah. So, threads have faster response time, creation is faster, and so on. POSIX document 13, that is real time application environment profile. So, this is what we are saying, that for embedded application the POSIX 4 is not very relevant, because these operate under constraints, and depending on the type of the application, 4 profiles have been defined. So, these are specific services to be supported under the specific environment profile. Now, let us look at the application environment profiles for embedded real time application. One is the minimum system, the one is real time controller. I think 2 more are there, we will see in the next slide. The minimum system is for the small embedded systems which have no memory management, no disk, no display terminal, keyboard, etc. So, these are the simplest embedded application. This is the operating system targeted for this, have to be POSIX compliant, have to be compliant to the minimum system environment profile. Next is the real time controller profile, which is something similar to the minimum system, excepting that there is a support for file system and input output, display and input. And here the real time controller has only one process, but there can be multiple threads. Only a single process is allowed, but multiple threads. Then we have the dedicated systems. These are larger embedded systems with no files. And then another environment profile is the multipurpose system, which is actually the POSIX 4. The entire POSIX 4 is for the multipurpose profile, but the others are for smaller applications, specific applications. So, we look at the POSIX 4 extension, the real time services that are to be proposed, and that will also give us an idea about what are the standard features required for a real time operating system. We had seen so far that what is expected of a real time operating system. This will actually reinforce that. We will see what the real time POSIX standard specifies, and that will also give an idea of kind of services that a real time operating system for specific application need to support. So, we will just stop here, we will continue in the next hour.